the recording. Okay, so so in this slide is basically I think 339 you guys already done for this PN junction diode, but you can treat this one as the review for the 339. So I'm gonna follow this step and then try to calculate the electric field and potential, especially in the space charge region. So in this specific example, we're going to look at the PN diode. As you can see, PN in here. The P side we dope with Na, and then the N side we dope with Nd, right? Okay. Now, the first step to look at the electric field, we need to start with the so-called Poisson equation, as we discussed in the last class. So Poisson equation basically give us a relationship between the electric field and then the total charge exists in the space. Okay. So as you know, in the semiconductor, we discussed the 4 different charges exist in the semiconductor. 2 of them coming from dopant. Nd is the N-side dopant. Na is the P-side dopant. And then corresponding their electron hole. So for example, if you have Nd, that produce electron. If you have Na, that produce the hole, right? So hole, electron, those two we call the mobile charge. Nd, Na, we call the immobile charge. Okay, so these are all the available charges within the semiconductor. Okay, so we need to solve this equation to calculate the electric field. And then another one is, as I mentioned, related with doping and then corresponding depletion width. So especially this 1D case in here, 1D means that we only just look at this X direction. In fact, in the real device, you're gonna have X, Y, and Z 3-dimensional configuration. But for this particular example, we just only look at the X direction to simplify our description. So for this 1D case, based on the doping and the depletion width, it has this kind of relationship in here. So in other words, if you have doping Na and D, and then their corresponding depletion width following this relationship. So as you can see is that when you have a PN junction diode, you have the dopant Na and D. They are typically given for the device. And then from there, sometimes we're looking for the corresponding depletion width. So as you can see, if you obtain either side of depletion width, then simply using this relationship, you can obtain the other side of depletion width. Okay, so this is also useful equation describing those relationship with doping and the depletion width. Now, as a first step, we did in the last class, we're going to split the location of the charge. Okay, so as you can see from the graph, especially between the x equals 0 to x equals Na, xn in here, you can see that in here, the number of charge is, we can put this one is Nd, right? And then the ND represent the number of charge, and then Q represent each charge, right? So this one is the charge going to be Q multiply ND in here. So in this side is, if you look at the total number of charge, as you can see, Na is not there, okay? And then electron also is not there in the depletion region. Hole is not there. So you can neglect this 3 term. Only remaining part in there is Q multiply ND, right? So if we just used in this equation only Q multiply ND, then from there is if you just integrate both sides, then the solution for the electric field, we obtain this equation. C1 represents the coefficient to satisfy its boundary condition. So in here, the boundary condition we put at the edge of depletion region in the N side, your electric field going to be 0, right? So if we put that boundary condition to this obtained solution, then from there we obtain the coefficient, and finally we obtain electric field. So this is going to be first solution, electric field, especially in this area, right? So similarly, now is if you look at the electric field in this side, okay, P side. So if you look at the P side, total number of charge in the P side is, you have dopant, this one remain. So, and then the ND is going to be negligible. And then depletion region, you don't have a hole and electron, also negligible. So from there, your equation to solve going to be this one with a Q negative Na, right? So if we do the integration, both sides, within this depletion region, which represent in here, then the solution going to be is following the similar approach. We get the solution for the electric field going to be this way. Okay, so now you have the electric field in the N side, electric field in the P side you obtain. Okay, and then if we plot the electric field, as you can see, electric field going to be following this curve, right? And then the outside of depletion region, electric field going to be 0. So you have this kind of curve. And then the maximum electric field magnitude happens at this physical junction in here between the P and. So that one is when the x equals 0 happens. So if we put that one there, then from there we can define the maximum electric field going to be this one. Okay. Again, this one is following this relationship too. Okay. So from there is now we can rewrite the electric field in terms of Emax. Then we can write the Emax with the electric field with this equation in here. Okay? So that way we can obtain the electric field. Once we obtain the electric field, as you know, we can integrate the electric field for each corresponding this region. Okay? Then we can obtain the potential P side, N side, we can obtain. So if we plot this one, again, we can get the potential of this kind of curve. Okay. And then if we add these two potential, we can also have this combined potential across the PN junction diode. And then in fact, this one is the same as the VBI we discussed before. Okay, so that way is that we obtain the electric field potential within this PN junction diode. Of course, in here, one thing you have to be attention to this charge distribution within the depletion region. In here is that we apply the charge distribution, saying that within the depletion region, you will have this constant charge, and then abruptly change, and a constant charge across this PN junction. Okay, this is what we call the step junction, describing this step-like charge distribution. So based on this assumption, we obtain the electric field and potential. Okay. You may see the other case is that instead of this step junction, we may have the different distribution of the charge. Okay. So for example, let's say your charge is kind of linear, or a different formula for this charge. Okay, so for that case, now is that in this charge distribution, you may have a certain function of this charge in terms of x. For example, linear case, we can have ax or something, right? But still is that the procedure to obtain the electric field and potential, just following the integration of these two sides, and then obtain the electric field and potential. Okay, so procedure going to be the same for that case. Okay, so that way is that we obtain electric field and potential. And then, as I mentioned, is that the potential difference in here, that gives us this VBI, built-in potential. Okay, and then in terms of Emax, also we can have the built-in potential for this particular case. We have this kind of formula in here. Okay, again, this formula is that still we assume is that charge distribution throughout the PN junction is a step junction. Okay, so that when you look at the potential, so in our case is that this is we define as the W, depletion width, and then as you know, this is the Emax, right? Of course, this is still negative in here. When you have the potential throughout this electric field, as you know, we integrate the electric field, right? That gives us our VBI. So integration means that the area of this electric field in here. Okay, so simply the area of this electric field, that one going to be is as you can see, is a negative Emax multiply W divided by 2, right? So that's the same conclusion we obtain from this equation. Okay, and also PN junction diode, one of the important parameter going to be depletion width. Okay, is we put as the W. Depletion width is going to be in here, as you can see, in the P side depletion plus N side depletion width. That's going to be total depletion width. VBI, as I mentioned in the previous equation, using this equation, you can obtain the VBI. Okay. And then the doping and the depletion width will follow this equation in here. Okay. And then individual, this depletion width, for example, in the P side, we can use this equation, which describes that you're doping with a VBI. You can calculate this one. Okay. VBI also is, as you know, in the previous is that we have the equation describing the VBI in terms of doping, right? So using that equation, we can also obtain the VBI. Okay. And then once you get the P-side depletion width, simply using this equation, you can obtain the N-side depletion width, right? So following this relationship. So from there is you can obtain the total depletion width, W. And then W related with this equation. Okay. So this one described at the thermal equilibrium is using the VBI and doping, you can obtain the thermal equilibrium, this depletion width. Okay. Now, in this slide is I'm going to describe the current flow in terms of our energy band diagram. Okay. So the first is that when you look at the current in here, so especially this energy band diagram. Okay. So when you look at this energy band diagram, I have a question in here. Okay. Is this thermal equilibrium?
No, Professor.
Okay. So no. Any other opinion, or why?
I would say because it's reverse bias.
Okay, Thomas say not with a bias. So how do you know this is not with a bias? Okay.
Professor, this is thermal equilibrium because the Fermi energy is constant throughout.
Yes, that's going to be a correct answer. So if you look at this energy band diagram, especially the information is in this Fermi energy level. So if you look at the Fermi energy level is constant throughout the structure. So we say that this is basically no bias applied. And then at the thermal equilibrium, right? Okay. So that is the correct answer. So now at the thermal equilibrium, as we discussed before, at the thermal equilibrium, initially is that when you have p-n diode, as we discussed, let's say at the moment we create a p-n diode, p-n junction, for example, in reality is cannot be done. Let's say if we are able to create this p-n junction at some point, and then at moment, as you know, in the p side you have lots of holes, in the n side you have lots of electrons. So by this concentration difference, hole is moving to the n side, electron moving to the p side, and then they're going to recombine. Okay? So while they are moving like this due to the concentration difference. In other words, by diffusion, they're going to start to create the electric field within this depletion region, because in the N side, for example, electron goes to P side, so that area loses the electron, so which means that now that developed this positive ionized charge within the depletion region in the N side. Same way in the P side, hole moved to the N side, so that developed the negative, this ionized charge in the P side. So when they create this positive, negative, they are separate in space, then they start to create the electric field. Okay. So when they start to create electric field, this electric field is now preventing further this diffusion. And then at some point, they reach to the thermal equilibrium. Okay. And then this energy band diagram is basically describing at the thermal equilibrium this p-n junction diagram. Okay. Now, on top of this energy band diagram, I just draw graphically distribution of the electron and hole. So for example, in the N-type semiconductor, as you know, we have lots of electrons available on the top of conduction band. So roughly I draw the number of electrons with these red dots in here. So as you know, most of the electron remain close to the conduction band. Okay, and then when we go up from the conduction band, as you know, the number of electrons going to be smaller. Okay, so roughly we can describe this distribution of electron in this way. Okay. Same way is that if you look at the p-type semiconductor, now you have lots of holes available in the valence band, and then most of the holes remain close to this valence band. Okay, and then if you go this way, now its direction of the hole energy increase, the number of this hole going to be reduced. Okay, so roughly we describe this situation in here. Okay, now is before we moving to the bias condition. In here is that I just define is that the thermal equilibrium. Okay. So thermal equilibrium means in the p-n junction diode, each electron current, so for example, electron current you have from the diffusion plus you have from the drift, right? So if you add them together, the total electron current going to be 0. Okay. Same way, if you look at the hole current also has diffusion current and drift current. If you add them together, the total current going to be 0. Okay. And then the diffusion and then the drift, as we described before, is we define that those current, right? So for example is that in the P side is that you have lots of holes. So hole moves this way, that create the diffusion of the hole. Electron in the N side then moves to the P side, that create the diffusion of the electron, right? And then once they have, you're gonna start to create the electric field within this region. So due to the electric field is that any electron exists in here now is moving this way. Okay. Hole within this electric field region then moves the opposite way. That creates the drift current. Okay. So that way is that you describe this Hall current and electric current. And then the second one is, again, as I explained, is that when the diffusion happens, at some point electric field is going to be created from N to P region, right? Same way as I explained. And then the carrier density is, as this is from 339. So when you look at the particular this carrier density, so for example, in the N silicon, the carrier density we can calculate from the product of density of state function and the Fermi-Dirac distribution, right? So we multiply these two function, and then we integrate above this conduction band. Then from there, we can calculate the electron distribution. Right? So that way, we can actually look at the exact number of those electrons and holes. Okay? So that is we describe at the thermal equilibrium. So now is go back to the condition that we apply bias in the PN junction diode, right? This particular PN junction diode is, as you can see, is that we apply the bias. Okay, so another is a similar question in here. Okay, so obviously you can know. How do you know this is the case we apply bias? So any answer from you? Okay. Okay. So if you look at in here is, as you can see, oh, this one is not mentioned, the EF. Okay.
Yeah.
So EF in the N side and then EF is P side. They are actually is not in the same level, right? So that is the indication of the biasing in the PN junction diode. Okay. And then second is, if I ask another question is, in the P side, do we apply positive bias or negative bias based on this energy band diagram?
Positive.
Positive, right? Because, so why, Kayo, you made that conclusion?
Because as you previously mentioned, I think that for the electron energy, every any kind of bias towards the electron energy would be positive. And for the whole would be negative, I think.
Okay.
Professor, can I maybe?
Yeah, Mika.
Yeah, so I want to say that I remember from last lecture, we talked about the reverse bias and forward bias, and you said that when the potential, the positive potential, if it's going to be connected to the P side, then it's going to go up. So that's why we see the electron energy being up. So it's in the forward bias position, right?
Okay, but in particular is, as you know, is in here is that as I mentioned, is that we see first, the Fermi energy level is not aligned, right? Throughout the PN.
That's correct. Yep.
And then which side Fermi energy level is lower, for example?
The left side, the P side.
Left side, right? So, and as you can see, that means that, as you remember, when you apply the more positive bias, the energy moving in this direction, lower direction. Okay? And then when you apply the negative, is the energy moving upward. So if you look at this energy band diagram, especially the location of this Fermi energy level, you can see that the Fermi energy level in the P side is actually lower than the N side. So which means that we apply the positive voltage in the P side for this particular case, right?
Mm-hmm.
So can you understand, everyone, is why this energy band diagram represent the P side is positive bias? Okay, so because this is the important concept, so if this is not clear, then always you can ask me. Okay, Jane Lee, you have a question?
Yes. So when we say we apply positive or forward bias, that means that we are introducing the holes. I just want to make sure that I'm not getting it.
Oh, so when we say that the forward bias, especially in the PN diode, when you apply the positive bias in the P side, that's we call the forward bias. So that's the kind of definition we use in the PN junction diode.
And that would mean the introduction of holes to the semiconductor?
Not that one is related with that, but I think at this point, if we just look at the energy band diagram in here, the first step is we just understand that is in terms of energy band diagram, EF going to be split in this way. So in the P side is that the EF is lower than this N side EF. So that's I think the first step you need to understand.
Yes.
Okay. So then again later on I'm going to explain is that when this one happens, you may see that now when this one happens, in fact this barrier height is lower compared to the previous case. So in the previous, if you go back, this is we call the thermal equilibrium, and then no bias, which means that your EF in the P side, EF in the N side, they are in the same level, right? So that indicates that this is the no bias applied through this PN diode, right? So for this case, as you can see, you have this one is we define as this is a Q VBI, built-in potential, we define in here. Now, if we apply the positive bias in the P side, if you apply the positive bias in the P side compared to this N side, EF, they need to be split, right?
Yes, then that would mean that
that means that this one going down,
lower, right?
Right. This one is going down. So when this one is going down, then now is, as you can see, this difference is changed VBI minus VA. Okay, so which means that this energy difference between this side and this side is lower than the previous case. Okay. So now, when this is lower, then now is interesting happens. The first is, as you can see, previous case is that the energy was this barrier is high, so that only certain electron or hole they can diffuse through this structure. Okay, but now its energy is lower, so lots of this electron hole they have enough energy so that they overcome this barrier. So that contributes the diffusion. Okay. So one thing is, as you can notice in here, is when you apply the forward bias, which means that we apply the forward bias in the p side positive bias, then your barrier height across this depletion region is lower. So you're going to start to create a lot of diffusion. Okay, and then this diffusion create lots of diffusion current. So in here is that the hole is moving in this direction. So diffusion current we define as in this direction. Okay, electron is moving in this direction. When you define the current, current is that opposite of the electron movement. So we can define the lots of diffusion current is flow in this direction. Okay, so that's going to be first observation in here. Second one is now in terms of electric field. Okay, so in terms of electric field in here. Okay, let me ask another question in here. Does this electric field increase or decrease when you apply the forward bias? Okay, so Thomas say decrease. Okay, then why do you think so? Okay, because forward bias create the opposite field. Okay, that's also part of the reason. Okay, another one is, as you remember, is in the previous class, you may remember that in terms of energy band diagram, electric field related with the slope of the energy. Okay, so in the previous class, let's maybe go back to the previous slide. Yes, probably you remember this equation in here. That this equation represents your electric field related with the slope of energy band diagram. Okay, so in other words, if the energy band diagram is something like this, it's a flat, okay, then you know that the electric field is going to be zero in here. Okay? If we have this is x direction. Okay, if you have a certain slope in here, now that magnitude of slope give us the electric field strength. Okay. So if we go back to the slide in here. Okay. The slide in here, so originally, as you can see, you have a slope of this energy band diagram, right? By applying the forward bias, you will see this slope is not abrupt compared to the previous bias, previous case at the thermal equilibrium. All right. So your electric field strength in here is lower compared to the previous case. Okay. So that indicates now, if you look at the current from drift, in other words, coming from the electric field, this one going to be smaller compared to the previous case. Okay, so that kind of thing is you can understand from this energy band diagram.
Professor, quick question.
Yes.
So the intensity of the electric field decreases. What about the width or the size of the electric field?
You mean the depletion width?
Yeah, the depletion width. Yeah.
Depletion width is actually decreased. Okay. It's actually following that, as you can see, is something like this. If you when you apply the bias, this VBI is changed to the VBI minus V applied bias. So corresponding to that is your depletion width is actually decreased too. Okay.
Okay. Thank you.
Okay, that's good. Yeah, if you have any question, yeah, just feel free to ask any question. So that way, maybe I can also check whether you understand correctly, and also you can understand better. Okay. So yeah, don't be shy. Just ask any question. Stop me. Okay. Okay. So that's the kind of is forward bias this case. And now another thing is that you can clearly understand is Hall diffusion current is in this direction, right? Because when this is lower, Hall moving in this direction, so Hall current is same direction. Electron moving in this direction, so electron diffusion current in this direction. Okay. Now is that the drift current. Okay. Drift current is, as you can see, electric field is in this direction. So in other words, is that this side you have positive, this is negative in terms of potential, right? So that creates the electric field in this direction. So whenever you have a hole in here, okay, within this electric field region, the hole is moving in this direction. Okay. So when the hole moving in this direction, that creates your drift current is in the same direction, in this direction. Okay. When you have, instead of a hole, when you have electron within this electric field region, electron is negative charge, so that moves to this positive side of this potential. Okay. So when the electron moves in this direction, as you can see, we define the current in the opposite direction. So your electron drift current is in this direction. Okay. So that kind of thing is you can actually see from this energy band diagram. Okay. Now, if you look at the total current in here, so let's say if you look at the total current going to be electron current, and also is plus you have Hall current, right? And then each electron current, you have drift current and then the diffusion current. Hole current also is diffusion and drift current. So let's say if you look at the electron, drift current is in this direction, diffusion current in this direction. The magnitude of diffusion current is now is larger than the drift current. So your total electron current is now in this direction. Okay. Same way, if you look at the total hole current, hole diffusion current is in here, drift in here. Diffusion current is larger than the drift current, so your total current is now in this direction. Okay. And then that represents this hole current. So for this case, as you can see, as you have the more forward bias in here, your diffusion current is getting stronger than your drift current, so that you're going to start to see lots of current through this p-n junction diode, and that contribute by the diffusion current. Okay. So that you can understand from this energy band diagram. Okay. Okay, that's good. Now, this is the opposite case. So this is we call the reverse bias. Okay, and then corresponding energy band diagram is I sketch it somehow this way. Okay. Now, if you look at this energy band diagram, this is N side, and this is the P side. Okay. So obviously, is the first question is I can ask in here is, how do you know this is the reverse bias condition? Okay. So then your answer going to be, what is your answer? So your answer going to be in here is, when you look at the Fermi energy level, first of all is P side and then N side, their Fermi energy level is not in the same level. And then P side, EF is higher than this N side. Okay, which means that this kind of change created by you apply the negative bias in the P side. Okay. So that's what we call the reverse bias, and that's going to be answer for that question. Okay. Now, for this particular case, when you apply the reverse bias in the p-n junction diode, as you can see, is a P side, this Fermi energy level is going up compared to the N side in here. That created now is that when you look at this barrier, the barrier, this one is when you apply the bias, you define that the VBI minus you apply the bias. Okay. Now, since the P side is negative bias, your barrier, this one, is larger than the case in the thermal equilibrium, right? So if you look at that case in here, because this barrier is compared to the previous thermal equilibrium is much larger, so now this diffusion is actually blocked by the high barrier, energy barrier. Okay, so this one effectively reduces the diffusion current for the hole and then for the electron. Okay, so your diffusion current going to be substantially decreased in here. And then when you look at the electric field in this structure, now is that the slope of this energy band diagram is larger than the thermal equilibrium case. So, which means that the electric field is much higher than before. Okay. And then this one now effectively increased the drift current. Okay. But in here is one thing we have to consider is when you look at the drift current related with the number of electron or holes. So for example, if we look at the hole drift current, this one related with the number of holes, and then the mobility, and then the electric field strength. Okay. Now, mobility is almost same, is fixed in the material. Electric field is now is increased. Okay. So obviously, for the same number of holes, we're gonna see that the drift current going to be increased. Okay. But in fact, within this depletion region, is typically we do not expect is the stationary, those electron holes exist within this depletion region. So only contribution of the electron hole in here is at the edge of the depletion region. You may have a certain minority carrier. For example, in the N side, the hole is close to this depletion region and start to see this electric field. Then they are going to be shifted by this electric field. Okay, so those electron hole contribute this drift current, and then typically this electron hole is number of this electron hole is very limited in the structure. So even though you have the increase of the electric field, so that it increased the drift current, but that increase of drift current is not significant for this particular case. Okay. So typically, when you look at the total current for this case, especially reverse bias, you're going to start to see that when you apply the reverse bias, you start to see slightly increased of the current, but that increased current is not dramatic, okay, compared to the forward bias case. Okay, so that's the case for this reverse bias. So this is the kind of summary is what we discussed. PN junction diode is we apply the different bias. So first, no bias is this is we define as thermal equilibrium. And then when you apply the P side positive, this one is we call the forward bias. When you apply the negative in the P side, that we define as the reverse bias in the PN junction diode. Okay. So at the thermal equilibrium, as we discussed, total current in here going to be 0. So when you look at the whole current, diffusion, drift, they are going to be opposite direction. So that when you look at the total current, that total current going to be 0. So same way, if we look at the electron, diffusion, drift, they act opposite direction. So total current of the electron going to be 0. Okay, so that's the case is that at the thermal equilibrium. And then when you apply the forward bias, as I explained, is that you're going to start to decrease the barrier height between the PN diode. Okay, so when the barrier height is decreased, you're going to start to see lots of diffusion current. Okay, so you have a hole diffusion current and electron diffusion current. But the drift current because electric field is now decreased, so you're going to start to see that the drift current is decreased. Okay. So that's the we can observe when you apply the forward bias in the PN junction diode. When you apply the reverse bias now, your barrier height is going to be increased. Okay. So the increase of the barrier height effectively reduce the diffusion current. Okay. Hole diffusion and electron diffusion current substantially decreased. Now you're going to start to see a little bit increase this drift current because your electric field strength is increased. Okay. But the available this electron hole still they are limited in this case, so you will not see the dramatic increase of this current. Okay, but still this you can see is a slightly increase of the current through this drift current. Okay. So considering this discussion, this shows the typical current versus voltage characteristic of a PN junction diode. Okay, so when you apply the P side is the positive, that's the forward bias. So when you apply the forward bias, initially you'll see that you're going to start to see the increase of current. Okay, and then when you approach close to the so-called turn-on voltage, you will see that the dramatic increase of the current. Okay, and then typically this turn-on voltage, on voltage, that one related with your VBI. Okay, so when your voltage is forward bias, is voltage close to the VBI, you're going to start to see lots of current flow. Okay, so that describes that so forward bias condition for the PN junction diode. Now, when you apply the reverse bias, which means that in the P side you apply the negative bias compared to N side, then now you're going to start to see is that the increase of current, but that increase of current is very, very limited in here. Okay, and then this current is mostly coming from the drift current. Okay. And then at some point, you are not discussed at this point, is that if this reverse bias is too large, then now device reach to the so-called breakdown. Okay, and then this area is we're going to study in the next chapter. Okay, so anyway, is that so far we just discussed about the forward bias case and then reverse bias this case. Okay, and then based on that description, is we can define that roughly this kind of IV characteristic of a PN junction diode. Okay, so that is the kind of basic description of PN junction diode, and then how the PN junction diode flow current when you apply different bias. Okay. So far, can you follow me?
Yes, Professor.
Okay, then that's good. Okay, that's good. So now is what we're gonna do in the following slide is that we try to actually lay down the theoretical derivation of this PN junction diode. Okay, so we can briefly, is in the previous slide, we discussed about the IV characteristic of PN junction diode. Now, based on this assumption in here, we try to derive the theoretical current versus voltage characteristic of a PN junction diode. Okay, so that's what we're gonna do in the next following slide. Okay, So to do that, in here is that we say ideal diode, okay, which means that for this ideal diode, we made several assumptions. Simply, we tried to simplify our discussion in here. Okay, so the assumption in here we have is, the first one is, let's say in the space charge region, so in other words, in the depletion region, let's say we have so-called step junction. So step junction is, as we discussed, if you have the PN diode, you're going to create the depletion region. Okay, and then especially when you look at the depletion region, the charge distribution, you will get the, let's say, this kind of step. Step shape of distribution. Okay, so that is the first assumption. Okay, we have in here. Second assumption, this one is within this space charge region. Okay, we assume is especially in here is the mobile carriers exist. So especially this one means you have holes, you have electrons. They cannot be within this space charge region stationarily, which means that the electron hole, at some point, they can go in within this space charge region, but due to the electric field created in this structure, those electron holes going to be swept out from this depletion region. Okay, so no stationary electron hole exists within this space charge region. That's the second assumption. Okay, and the third one is in the bulk of the diode, which means that outside of this depletion region, okay, we assume the semiconductor is neutral. Okay, so in other words, is that you have p side. If you look at the total number of charge, this one in the p side, that's going to be 0. Okay, same way if you look at the n side, total number of charge, if you look at there, that's going to be also 0. Okay, so that means in here is we treat as a neutral. Okay, and then the fourth this assumption is when you operate this diode, the diode is operated within the temperature where all the impurity atoms are ionized. Okay, so which means that when you look at the energy band diagram, it's probably this one also related with 339. You may heard that this is the EV, this is the EC, energy band diagram. When you dope this one with N-type dopant, okay, so ND, when you dope with ND, the ND energy level is located is close to the EC. Okay, so at the temperature is 0 Kelvin, you will see that the electron is located on this energy level, dopant energy level in here. Okay, so at the T equals 0 Kelvin, and then if you look at the total number of electrons available for this N-type silicon in here, the number of electrons going to be very, very small in here. In other words, is the conduction band is number of electrons going to be very, very small. Okay. Now, when the temperature, this one is going up, reach to the this close to the room temperature, then those electrons which located in this dopant energy level, they have enough thermal energy so that they can jump to this conduction band. Okay. So that now this condition is that if you look at the total number of this available electron in the N-type silicon, that is close to the dopant, number of dopant. Okay. So that is the condition is that we have in here. Okay. So operation of this p-n junction diode is that all the impurity atoms are ionized so that they contribute the electron or holes from their doping. Okay. So when we look at the characteristics theoretically, when you have the N-type silicon that dope with Nd, we assume that the majority carrier number is the same as the UO doping. Okay, so that kind of theoretical is assumption we can make based on this assumption in here. Okay, and then the fifth one is at this point we didn't study yet, but as you can see, is that when you have a p-n diode, okay, when you have p-n diode, and we often say that we can apply the bias from outside, right? Okay. Now, when you apply the bias, is typically you have, let's say, battery or power supply, which has the electrical metal contact, okay, to this p-n diode. So p-n diode, this is a semiconductor. And then you have some metal going to be connected to this edge of this p-n junction diode, okay, to form this circuit. Okay. At this point, we didn't discuss about that how this metal plus this semiconductor create its interface. Okay. So we just assume that this interface between the metal to semiconductor, that is perfect, which means that when the current flow through this interface, there is no discontinuity happens through this interface. That's we call the ohmic contact. And then in here, we assume that we achieve this perfect ohmic contact for this p-n diode. Okay, but in the later chapters, at some point, we're going to also study about the metal to semiconductor this junction. Okay, so as you can see, when we say the semiconductor, even silicon case, you have N-type silicon or P-type silicon, and then you have different doping level, right? Same way, when you say the metal, you define that this is the copper, this is aluminum, or silver, gold, platinum. You have all the different this metal, right? So which means that each metal we define as the different material characteristics, okay? So those different material characteristics create different this metal to semiconductor interface. So later chapter, we're going to study those interface later on. But that's it. At this point, especially this beginning of this p-n junction diode, this discussion, we can just assume that we don't have any interface, especially current flow through this metal to semiconductor. Okay, so that's the meaning of this perfect ohmic contact. Okay. And then another one is a 6, this one. When we operate the device, we initially discuss about the device is only operate within the so-called low injection, especially is a forward bias of the diode. Okay. the definition of the low injection is later on, is we're going to define this one. Okay, so, and then the last assumption in here is, especially in the depletion region, okay, so when you look at the depletion region, within the depletion region, there's no recombination or generation takes place. Okay, this means that when you have the PN junction diode, okay, so when you have the PN diode, as we discussed, is that you have the depletion region in here, and then in here is that you have a hole or electrons, minority carrier, can be going in within this depletion region. Okay, so when, for example, when the electron going into the depletion region, that sweep out by the electric field and come out in the opposite direction. Okay, the same way is that when the hole going into this depletion region, that coming in and then coming out. Okay, so that if the one going into the depletion region and then eventually one come out. Okay, so that's the condition for this seventh assumption. Okay, if there's a recombination happens within the depletion region, maybe one goes in, but within the depletion region, it recombine, disappear, so it doesn't come out in the opposite direction. That's the recombination case. Another case is that one goes in, but this one creates another one within the depletion region, so that in some case, you may have two come out. Okay, that's a case of generation. Okay, at this point, for our case, we just look at the one coming in and one come out from this depletion region. Okay, so these are the assumptions we're going to use in the following slide. Okay, I think we're going to stop here because we only have 1 minute left. Do you have any question? So,
yeah, Professor, I have a question
yes,
about number 5 and the ohmic contacts.
Okay. Yes.
Is this the reason, like I guess the ohmic contacts not being perfect? Is that the reason for there to be capacitance inside of like MOSFETs and BJTs and things like that?
No, it's different story. Is that the capacitance is that, as you know, is physically we define as when you have a certain structure which separate the charge. That is, we define the capacitor. Mm-hmm.
Yes.
So that is the different story with the ohmic contact.
Okay. All right.
But I think when we discuss the metal contact, we're gonna discuss more detail further this contact. So for the time being, maybe we can just assume such a way that the metal to semiconductor PN junction diode, there's no discontinuity happens.
Okay. All right. Thank you.
Okay. Okay. Thank you. Okay. Any other question? Okay. Then I think we're gonna stop today's class in here. So we're gonna meet next week. So be safe and then see you next week. Okay.